this video we'll be discussing the resonance of a parallel LCR circuit. So this circuit basically has an inductor and capacitor connected in parallel, and this whole thing is connected in series with your resistance. In addition to that, we have a milliammeter and a voltmeter, both AC devices connected to your audio oscillator. So that's your circuit diagram. And now let's talk about the principle. So in your parallel LCR circuit, when you have the resistance in the inductance arm and the current in the inductance arm will be equal to the current in the capacitance arm. So because of this, your impedance value, impedance being the net resistance offered to the circuit by the three components of the LCR circuit, which is L, C and R, is your impedance. So impedance is maximum in the parallel LCR circuit, because of which the current through the circuit is minimum. So now the output voltage and current will be out of phase, and then you can measure the resonant frequency at which impedance is maximum. And then you can also find the value of inductance, and then you can find the bandwidth. So bandwidth basically is the frequency range at which current value will be 1 by root 2 times the minimum current value. So if you see the model graph of this experiment, you will have a dip or minimum value of the current through the circuit at some particular frequency. Now root 2 times of that will be the bandwidth frequency range. So we'll be setting up the circuit now. So what you have in the circuit is a signal generator, which we have here. Then you have an inductor and capacitor in parallel, which we'll be connecting, and you have a resistance box, which is here. And then you have a milliammeter, which we've kept here. So what you have to do is, first you connect the signal generator across the milliammeter. The positive goes to milliammeter, the negative goes to the capacitor. Okay, then the negative of the ammeter will go to your resistance box. Then the other end of your resistance box will go to your capacitor, the other end of the capacitor. And then finally you have to connect the capacitor in parallel with the inductor in parallel with the capacitor, like this. And that's all for your circuit. So once you're done with the circuit, you can start taking readings. So what we have to do in this experiment is, you have two trials with two values of capacitance, and you have a fixed resistance of 5 ohms, which we have removed. And what you need to do is, first you have to set the capacitance as to 0.2 microfarad. So you have to vary it over here. So it's 0.2 right now. And the second trial, you will do the same thing for 0.5. So what you do is, you start with frequency of 10 Hz on your signal generator. So it's set at 10 Hz, and you can keep changing the range to take your values. So we start with 10 Hz, and what you do is, you take the readings of your ammeter for every 10, 20, 30, 40 and so on up to 100 Hz. So you can change your frequency to 20 and then 30 and so on up to 100. So this is 100. So for 100 Hertz, you will have to write the change in the current value in the ammeter. Then you repeat the same thing up to taking 100, 200, 300 up to 1000 Hertz or 1 kilohertz. So this is for 1 kilohertz. Yeah. So for 1 kilohertz, you can see that your current value decreased to 21. So we started with 100 and something, and it decreased to 21. And when you go to around 2000 or 3000 hertz, you can see that the current will reach its minimum value. So this is for 2 kilohertz. Then now we have 3 kilohertz. So you saw that it decreased and it increased again. So you will have some minimum value of current. That will be your, so for me it was 4.7, but it could go lesser also. So that will be the bottom peak in your the dip in your graph. So you started with a high value of current, it dropped to some minimum value, and then it will increase again when you increase the current. Sorry, frequency. So now you were at 1.5 kilohertz, say. So you have to increase it up to 10,000 kilohertz. You have to repeat the same thing for every 1,000 hertz. Sorry, 10,000 hertz. So now you can see that it's at around 8.5 kilohertz and your current increased back to the initial value. So you repeat the same thing up to 10 kilohertz, and that's all for your tabular column. And you repeat the same thing for the second value of capacitance. So this was for zero point 0.2 microfarad. You have to repeat the same thing for zero point 0.5, and that's all for the tabular. For plotting the graph, you have to keep the paper in this orientation. And since this is a semi-log graph, it's very important in which direction and how much you increase the logarithmic scale by. So on your x-axis, you'll have values of frequency. So since we have to fit two graphs into this page, it's simpler to start with 100 hertz and then plot it as 100, 200, 300 up to 1000 hertz or 1 kilohertz. Then because it's a log scale, you have to plot it as 2000, 3000, 4000 up to 10,000, and that's about all the values we need if you can see the range in the table. Then you have to repeat the same for the second graph on the right of that. And on the y-axis, you'll have the values of current in milliamperes, and that you can plot as 5, 10, 15, 20 because you don't have that much of values. Then when you plot the graph, you can get the shape like this. Then you have to identify the minimum current value, which you can also see in the table if you notice. Then when you identify that minimum current value for both the graphs, you have to multiply that by √2 to get the bandwidth frequency range. And that's all you need from the graph. Finally, for the result, you have to calculate the value of L for both the C1 and C2 capacitors. And when you find L, that will be the result. And then you get the mean value of the inductance of the coil from those two. Then you have to also find F naught for the two capacitance values. And you do not find mean F naught like I have here because it's two different resonance frequencies for two different circuits. But that's all for this experiment, and bandwidth you have to fill in from the graph.